What's going on, guys? Today I will be going over clone graph, and in this problem you're given a reference to a node in a connected undirected graph, and you're supposed to return a deep copy of the graph. So before we even get started, what is the difference between undirected and directed graph? So in a directed graph there's an arrow between one node to another, and in an undirected graph you can just visualize it as basically two arrows pointing to each other. So if you go from one node to the other, there's a way you can get back as well. It's also important to note the difference between pass by reference and pass by value. So this is where the whole deep copy comes into play. So if we were to instantiate a node, let's say A equals node, and we give it a value of, say, 5. If we were to visualize that, we would see something like this. A node with a value of 5 with A pointing to it. Now, if we were to have something like B equals A, we would have B pointing to this node. So what this is B is a shallow copy of A. What it's asking in this problem is to return a deep copy. So what you really want is not this, it's what you want another node like this with B pointing to it. So each pointer A and B are pointing to separate places in memory. Each node will have a value and a list of neighbors. So the value will be an int, and the list of neighbors will just be a list of nodes that are connected to that current node. And for the purposes of this problem, the values in the nodes are unique starting from index 1. So basically the value represents the unique identifier of the node. As our input, we're given one node object, so that's our starting node. And you have to keep in mind that since we're only given one node object, we can only access the node and its neighbors. So we have no idea what the rest of the graph topology looks like. So we start here, we can see that there's this starting node and it has two neighbors, 2 and 3, but we don't know 4 exists yet. The way we want to be solving this problem is doing a depth-first search. And so basically, at depth-first search, you recursively search through all the nodes. So you travel to one node, and then you travel to all its neighbors, and you travel to all its neighbors. And while you're doing that, you want to be keeping track of all of the visited nodes. So then you don't repeat a traversal and go back to a node you've already visited. What we want to be returning is an exact replica of that node and its underlying topology. So what we want to be returning is an exact replica, which is displayed here. The way we want to be doing this is starting our DFS at this point, which is 1, and then once we do our DFS, we clone the graph. So I'm going to represent the clone graph in blue here. And we also want to map the pointer in a hash table. So we want to map the original node to the node you just cloned. And the reason why we do that is because we want to be returning a copy of the node, not the node itself at the end. So we'll do the mapping here. So the original node maps to the cloned node. So keep in mind, this may say 1 here, but this is actually the node itself. And so think of this as like a pointer to the node in memory. Continuing on with the DFS, we're at 1, and we can either traverse to 2 or traverse to 3. So let's just traverse to 3 in this case. And what we want to do is we want to create that link, and we want to see if 3 is in the visited table or not. We see that it's not, so then we create it. So now you have to keep in mind that this is a undirected graph, so we can either go back to 1 or go to 4. So since we see that 1 is already in our visited table, we can DFS there, but we would return immediately because the 1 is already in visited. So let's go to 4 here. We do the exact same thing. Oh, so keep in mind we should be adding these to the hash table as we go along. So we have 3 now. Now we go to 4. Let's create that 4 and add it to our hash table. This is a 4 here. And now, same thing, we go to 2, create that link, create that clone 2, and add that to our hash table. And now we go to 1, we see that 1 is already in our visited table, so then we can end our DFS there, and basically what it will do is it'll propagate backwards until we reach the starting point, and at this starting point we return that mapped value. So time complexity of this algorithm will be O of n, and this makes sense because you have to traverse through every node. Space complexity will also be O of n, and this makes sense because you have to create that hash table mapping from the clone nodes, from the original nodes to the clone nodes. So very first thing we do here is we can check to see if the node is null or not, and if it is null we can just return node, and node in this case would be empty. And here's where we actually do our DFS. So we instantiate our DFS, or we have a visited hash table here, and then we want to call DFS on the starting node. And what we want to first check is we want to see if that node has already been visited. If it has, then we return the mapped value. So the mapped value would be whatever the cloned value is. And otherwise, we can create a clone for the given node. And this is what we do here. And we then add that clone into our visited. We add that mapping, right? So our node maps to the clone node. And now we want to iterate through all our neighbors and basically continue on with the DFS here. So we loop through every neighbor and we do clone node.neighbors.append DFS neighbor. So what this does here is it actually creates the link. So this is what adds it. This is what adds the link in the clone nodes, and basically what it's adding is the DFS result. So remember what we're returning here is the mapping. So we would be mapping the return values of all the DFSs. I know in the diagram I showed you, I was creating the links as we went along, but in the actual code, we are actually creating those links after we do all of our DFSs. So we do all of our DFSs, we would propagate backwards and create all of those links, and then return the clone node at the end.